Hello student, so this is the part 2 of basics of crystal structure. So in the last class we have discussed about the crystal structure, unit cell, primitive unit cell vectors. So now today we start from Bravais lattice. In the previous lecture we have discussed about lattice. Now what do we mean by a lattice? A lattice is a periodic arrangement of infinite array of geometrical points which looks similar when I view it from one point to the other. Now Bravais lattice is a special kind of lattice. Here not only the points are the geometrical points are arranged in the similar way, but their orientation also remain the same. For example, if I consider these points, if from the orientation point of view, the point P and Q are identical. However, the point R is different. So this is not a Bravais lattice. So what is the definition of a Bravais lattice? A Bravais lattice is an infinite array of discrete points with an arrangement and orientation that appears exactly the same from whichever point the array is viewed. So here we have one extra term which is orientation. For example, here orientation wise P and Q are identical but not R, so that's why this is not a Bravais lattice. Now Bravais lattices satisfy certain symmetry conditions. These symmetry conditions are beyond the discussion of this lecture, so we will not discuss about these symmetry conditions. Considering all the symmetry operations like translation, rotation, etc., there exist only 14 ways in which the points can be arranged to form a lattice. These are known as Bravais lattice. So in 3-dimensional there are only 14 ways in which geometrical points can be arranged so that they look similar when they are viewed from any point, and their orientation also remain the same, and also they satisfy certain symmetry conditions. This is the definition of Bravais lattice. Now as I said, there are 14 types of Bravais lattice. So there are 7 systems: cubic, trigonal, tetragonal, hexagonal, orthorhombic, monoclinic and triclinic, and for each of these systems there exist some types. For example, for cubic there are three types: simple cubic, body centered cubic and face centered cubic. Then trigonal, so for a simple cubic all the sides are equal and all the angles are 90 degrees. So this is the lattice parameter. For trigonal all the sides are equal but the angles are equal but not equal to 90 degree. For tetragonal, A equal to B not equal to C, so one side is not equal and all the sides are equal, and so on. Then the maximum types of Bravais lattices is found in the orthorhombic systems, in which A is not equal to B not equal to C and all the angles are 90 degree. Here are a few examples of materials which crystallize in this structure. For example, NaCl crystallize in cubic structure, CaCO4 it crystallizes in trigonal structure, and so on. These are the 14 types of structure. So this is simple cubic. There is one corner point at each of these corners. So this is simple cubic. All the sides are equal, all the angles are 90 degree. For this is also another cubic structure. However, here apart from these corner points, I have one lattice point at the center of the cubic. This is face centered, as the name suggests. In this, apart from these corner points, I have one lattice point at the center of each face. So that's why it is called face centered. We will not focus on the other types. Just keep in mind there are 14 types of Bravais lattice in 3D. In 2-dimensional also we have 5 types of Bravais lattice. These are the 5 types. So these are the 5 types of Bravais lattices in 2-dimensional structure. Now we will discuss in details about each of the cubic structure. For example, simple cubic, body centered cubic and face centered cubic. As I discussed, the simple cubic structure has one corner point at each of these corners. So there are total 8 corner points, and if I say this is my x axis, this is my y axis, this is my z axis, the primitive lattice vectors are a1 equal to a I cap, a2 equal to a j cap, a3 equal to a k cap. So these 3 vectors actually they identify this one and this one. All the sides are equal. And for body centered, I have one extra lattice point at the center. So for this, the primitive lattice vectors are a1 equal to a by 2 I cap plus z cap minus k cap, a2 equal to a by 2 z cap plus k cap minus I cap, and this is a3. Now what these vectors represent? These vectors actually represent these body centered lattice points. So in a body centered cubic structure, the primitive lattice vectors denotes or represent the body centered points. Similarly, for a face centered structure, I have one lattice point at each of these faces, and these are the primitive lattice vectors. These primitive lattice vectors actually represent all the face centered points. So these are the basics of this simple cubic, body centered and face centered. We will discuss in details about this structure. So this is simple cubic structure. Now, so there are 8 points. However, each of these points, if I consider each of these points are, for example, if I consider this point is shared by this unit cell, this point is shared by the unit cell opposite to this, one unit cell opposite to this in this direction, and one in this direction. So 4 unit cell is sharing this, and also there are 4 on top of this. So each of the corner points are shared by 8 unit cell. So one corner point is shared by 8 unit cell. So 1 by 8 corresponds to 1 unit cell. So 1 by 8 of any corner point corresponds to this unit cell. And there are how many corner points? There are 8 corner points. So 8 into 1 by 8. So there are total 1 lattice point in a cubic lattice. I hope this is clear to all you. Now, what is the volume of this conventional cell? So since all the sides are A, the volume is A cube. The lattice point per unit cell, as I discussed, 8 into 1 by 8. So 1 lattice point per cell. Volume of the primitive unit cell, there is only 1 lattice point in A cube. So primitive unit cell volume is A cube. Just remember, primitive unit cell volume means the unit cell which contains only 1 lattice point, and here A cube contains only 1 lattice point. So primitive cell volume is A cube. Lattice point per unit volume, obviously 1 by A cube. Nearest neighbor. So for one simple cubic structure, the nearest neighbor are 6. So if I consider this one, the nearest neighbor of these are 1, 2, 3, 1 in the bottom 4, 1 in the negative x direction 5, and 1 in the negative y direction 6. So these are 6 nearest neighbor points. Now nearest neighbor distance, the nearest neighbor distance is A, and the packing fraction, we will discuss about the packing fraction later on. Now for a body centered cubic structure, as I discussed, so this is the primitive unit cell vectors. These are the primitive unit cell vectors, and so here these unit the corner points adds to 1 lattice point. But however, there is one additional point at the center. So there are total 2 lattice point per unit cell in a body centered cubic structure. So there are 2 lattice point per unit cell. So this is not a primitive unit cell. So what is the volume of the conventional cell? Obviously this is A cube. Lattice point per cell is 2. So what should be the volume of the primitive unit cell? It should be A cube by 2, because A cube contains 2 lattice point. So I should divide a cube by 2. So it is a cube by 2. Lattice point per unit volume is 2 by a cube. Nearest neighbor, the number of nearest neighbor. So if I consider this body centered point, so I have this 1, 2, 3, 4, 5, 6, 7, 8. 8 points which are at equal distance. So I have 8 nearest neighbor, and the nearest neighbor distance is this half of the diagonal. So it's root 3a by 2, and the packing fraction we will discuss later on. Similarly, for a face center structure, now here so the total 8 corner points adds to 1 lattice point. However, each of these face centered points, they are shared by 2 unit cell, one this and one opposite to this. So each of these face center lattice point is shared by 2 lattice point, one this and one opposite to this. So half of each face centered lattice point corresponds to this lattice. And there are how many face centered points? There are 6 face centered points. So 6 into half is equal to 3, 3 plus 1. So 4 lattice point per unit cell in a face centered cubic structure. So what is the volume of the conventional cell? Obviously a cube. Lattice point per cell is 4, 1 because of the corner points, 3 because of these face centered points. Volume of the primitive unit cell is obviously a cube by 4. The density is 4 by a cube. Now number of nearest neighbor. So here the nearest neighbor corresponds to, if I consider this, the nearest neighbor points are these face centered points, and it can be shown that there are total 12 nearest neighbor points. And what is the distance? It's half of this this diagonal, the face diagonal. So it's a by root 2 or root 2a by 2, and the packing fraction obviously we will discuss later on. So this is all about face center cubic structure. Now packing fraction. What do I mean by packing fraction? It is defined as the maximum fraction of volume occupied by the constituents. Now when the lattice is filled with atoms, we consider the atoms are like hard spheres, and obviously when these hard spheres occupy the space inside a lattice, they some of the space got occupied, but some of the space remains unoccupied. So this packing fraction defines the maximum or estimates the maximum fraction of the volume occupied by the constituents. So it is measured. It is a measure of how densely the lattice points are packed. If V1 is a volume occupied by the constituents, then and V is the volume of the unit cell, then packing fraction value is V1 by V. Now let us consider this square lattice. Now in a square lattice, obviously if I have, this is a 2-dimensional case. Each of the sides are A, and these are the lattice points. Now if I want to add atoms, so here I have to consider the atoms like disk of say radius R, and if I fill them, so I can fill one here, one here, one here, one here. And if the radius is R, so I can see that R plus R, 2R is equal to the side which is equal to A. So the definition of packing fraction here is the total amount of space occupied by these disk divided by total area. So total area A is actually A square, and A1 is equal to the number of lattice point into pi r square, the area of one lattice point. So this is pi r square, the area of one atom. So it's pi r square, and A is A square as I discussed. Now here each of these corners are shared by 4 unit cell. So 1/4 corresponds to this. So total number of lattice point is 4 into 1 by 4. So 1. So here n is the number of lattice point in this structure. So n is 1. So if I put all these values, 2 are equal to A, n equal to 1, in this I get the packing fraction for this structure is 0.785. I hope this is clear. If you have any query, you write in the comment box. I'll try to resolve that one. Now similarly, if I have another structure, this is also a 2D structure. This is a centered square lattice. So I have one point here. So here, as I discussed for the BCC structure, there are two lattice points, one for these corner points and one for the corner points and one for the center. So there are total two lattice points, and how R and A, the radius and the atom, lattice constant A is connected. So I have R plus 2R plus R. So 4R is equal to A. So if I put n equal, so in this if I put n equal to 2 and 4R, so 4R is equal to the diagonal, so this is A root 2. So 4R equal to A root 2. So if I put all these values, so I can estimate the packing fraction. I am leaving this for you. Try to solve it at home and write in the chat box what should be the value. Now let us move to the three-dimensional structure. For example, a simple cubic. Now a simple cubic, we have already discussed the total number of lattice point is 1, and if I add this sphere, these spheres of radius r, I can show that 2r is equal to a and n. So obviously here packing fraction is n into 4/3 pi r cube, which is the radius, which is the volume of each atom. So n into 4/3 pi r cube by a cube. So if I put n equal to 1, which I have already discussed for simple cubic structure, and here 2r equal to a, we can estimate the packing fraction, which is of the order of 0.523. Similarly, for a body centered, now here my n, as I have already discussed, total number of lattice point is 2, so n equal to 2, and how r and a is related. So here I have r plus 2r plus r, so 4r equal to the body diagonal. So the body diagonal is a root 3. So 4r is equal to a root 3. So put these values, so replace r by this and a and n equal to 2. From this I can estimate the packing fraction value is around 0.680. Similarly, for face center cubic structure, as we have already discussed, n is 4, and here I have 1, 2, 3, so 3 spheres, and I have r plus 2r plus r. So 4r is equal to face diagonal, which is a root 2. So n equal to 4 and 4r equal to a root 2. If I put all these value, my packing fraction value will come around 0.740. So this is very important, that the packing fraction for the face centered cubic structure is maximum in compared to simple cubic and body centered. So it has the maximum packing fraction. That means the atoms are densely packed in this structure. The amount of denseness or it is more densely packed compared to a face centered cubic structure or a body centered cubic structure. Thank you. So we'll meet in the next video with some other topics of crystal structure. Thank you.